And I am a professor of chemistry and the coordinator and host for the spring 2025 season of the Bergren Forum. This is episode 1. Today's date is Thursday, January 30th, 2025. And for those of you attending the forum online, here in Western New York, it is a cloudy day, but one of the warmest days, only the second one where we're forecast to get over freezing over the last month kind of day. But inside Nevins Theater, the Powell Campus Center, it is cozy and the coffee and tea are hot and free. Before starting, we have a few announcements. First, next Thursday's forum will be given by Meg Bernstein. Meg's talk will be on an art historian's approach to stone carving. There are some other events this week to announce. Tomorrow evening from 7 p.m. until 8 p.m., there will be a mug cakes in the second floor lounge of Powell. This event is sponsored by the Student Activities Board. Come and have a free, delicious dessert. There will be a demonstration by resident artist Ashley Ray Harris in the Glass Studios on February 4th and 6th from 1:30 to 3:30, and a lecture in Binns Merrill, room 106, as part of the Black Glass Artist Series. Another lecture will be held on January 30th, that's today, at 4:30 by Eugene Agiei as part of the same series. My apologies if I mispronounce Eugene's name. Later today, Chase Angier will open an exhibition called Distilling Place from 6 to 7 p.m. in the Scenography Gallery of the first floor of Miller. Tomorrow night, and in fact every Friday night, there will be an open draw in the Brick Basement. Tomorrow from 12:20 to 11:10, the Herrick Bookend Lounge, the Women and Gender Studies Roundtable will hold a roundtable discussion on resistance, perseverance, and the struggle for change. Finally, for faculty, the class list verifications are coming due. Today's forum will be given by Rebecca Welch, visiting assistant professor of material science and engineering. The title of the talk is Glass, the most bizarre and coolest material on Earth. Take it away.
Thank you so much. Awesome. Hi, everybody. It's great to be here. Hi, Sean. Thank you so much for the invitation. First, I want to do a brief introduction since I am very new to Alfred, and so I don't think I know everybody, and people don't really know me, so this is perfect. So I did my undergraduate in physics from Coe College, which is in Cedar Rapids, Iowa. And during my time there, I did glass research with Dr. Fatigato and Dr. Brigado, who is actually now at Alfred as the newest ceramics professor in engineering, I believe. After my undergraduate work, I then fell in love with glass research so much that I was like, hey, why don't we just go to grad school? And so I went to grad school at Penn State, and I did my research with Dr. John Morrow, who is an Alfred alum. And I actually defended my PhD in May 2024, which was, yeah, it's been a big year. Okay. And then while my time at Alfred, so I began as a visiting assistant professor here just last semester, really. And during my time, I also was here for a whole year during my last year of my PhD program, doing it remotely. But I was really actively involved in Alfred during that time. And some of the things that I've done is I've been teaching 2 courses. Last semester, I taught thermal processes in materials, which is essentially an upper level thermodynamics and kinetics course. And then I've been teaching first year seminar for all of the incoming engineering students. And some of the other outreach things I've done, I am the club advisor for Alfred Society of Women Engineers, which was a completely dead club since COVID, but since then we've revitalized it. And our club is very active. This is a totally shameless plug for it. And we have about 40 members now. We go to conferences. This is us at the Society of Women Engineers Conference, which is held annually. This was in Chicago. And if I've learned anything from my undergraduate professors, it's that whenever you take students on trips, you always give them lots and lots of food. So this is us at this amazing Turkish restaurant in Chicago. It was about like a dish like this big of just meat. So we all had a great time. We eat a lot of food in our club. So please join if you're interested. You do not have to be a woman. You just have to support women in engineering to join. Something else that I've done during my time here at Alfred is I started the Night of Science and Arts. This has been going on for 2 years now. We just did it last semester, and it was a great time. The only reason why I'm telling you guys about this is because I need more volunteers, I need more demos, I need more departments to be involved, okay? So this is a one-night event. We have as many STEM and art departments come together as possible. We get all kinds of student volunteers as well as faculty volunteers. Right now we have about 60 demos, which is on the low side, but I'm hoping to get it up. And consistently now, we've brought in about 500 visiting children and families from the local community. So please, whenever you see emails about this in late summer, early August, it's from me, and it's because I really, really need more help. Okay, so going to our actual topic today about glass and why I think it's so fascinating and why I think it's a great topic. So something about glass is we've always been fascinated as humans with glass, right? Glass is such an important and pivotal part of our everyday society, but it's something that we don't really ever think about. It's just always there, but we never really realize just how influential glass really is. So hopefully we can kind of address that, and maybe we'll get a bigger appreciation for glass in our everyday world. So something that you need to understand about glass is predominantly something that is only made by humans. Like it only exists pretty much because we as humans make it. Now there are some forms of natural forming glass, but even with natural forming glass, they only exist under some of the most insane and extreme conditions, okay? So the first one here, obsidian, probably very common. Everybody knows what obsidian glass is. Well, you get obsidian glass from an active volcano from molten lava that has cooled. Okay, that is where you get obsidian. All right, so that's one form of natural forming glass. Another one, moldavite. This is a glass that is only formed from meteorite impacts. Okay, that's the only place where you'll find them. And then the last one, fulgurites. These are glasses that are specifically made when lightning strikes sand, okay? So all of these things, what they have in common is that they require extreme conditions to make, all right? So the fact that we as humans have been able to make glass so prolifically is really quite an achievement, actually. So a little bit of a history about glass, okay? So this is kind of argued because, you know, we're not really sure where it originated. Some people argue ancient Egypt, some people say Mesopotamia, but we know it's somewhere around 5,000 to 1500 BC, in which we have found remnants of glass being used, and it's mostly as decorative objects. So these are glass beads, and then we use them as vessels for a while. And from Mesopotamia, we know that we created glasses, but what's really interesting is back then, glass was so difficult to make that historians, they were able to find like these little instruction tablets on how to make glass. And on those, inscribed on those tablets is an entire instruction set of a ritual that the Mesopotamians used to have to do just to hope that they even make glass. And one of the things that they had to do is, you know, they take their sand or their rocks from their local environment, they put it into, you know, what they had as their furnace then. And before they even close up the furnace, they would pray to the gods, they would sacrifice a goat, and then close up the furnace and then just hope that they made a glass, okay? So this is where we really started, and it's because we really did not understand anything about glass. Since then, right, the Romans actually, fast forward, the Romans became really the first civilization to mass produce glass. And that's because they started to play around a lot with the chemistry. And one of the things that they did is they added fluxes to their sand or quartz. And fluxes is just like In our days, that would be like sodium carbonate, that would be like calcium carbonate. And what they found is when they added that, it would lower the melting temperature needed to make a glass, and therefore it became really easy to make glass, and it became really cheap for them to make glass as well. Something else that they did is they actually began to develop glass windows. Now, this seems like kind of a, I don't know, a minuscule thing, but like think about how revolutionary having windows were back then. What is the alternative? You have a hole in the wall? That's not fun. You have like dirt and everything coming in. People don't want that. The other alternative is you're in like a basement essentially, and you're like depressed because you don't have any light, right? So having just windows for the first time, it became such a huge part of our culture. And what's really kind of cool about this is that Western Europe, Romans, they were the ones that were really interested in making glass, trying to understand it, trying to make it better. While on the other hand, in East Asian cultures, there wasn't a focus on glass. They didn't really focus on trying to understand glass. Instead, they were focused on paper. So one of the main stark differences that you see in East Asian cultures historically, you see their windows have paper screens. They're not glass, right? And it's because these two different cultures focus on very different things. Okay, also the Romans started using pincers to help form the glass, and this actually led to the modern day glass blowing, which is why we have such amazing glass art now, right? So glass blowing became perfected by Italy in Venice, and then later in Murano in about the 12th century, and that really became the hub for glass blowing. And that's where we get these amazing cathedral glass, these amazing stained art glass pieces. Now, what's really cool is because we were getting really good at manipulating glass, that doesn't mean we didn't really understand it per se, but we're really good at manipulating it and making it now. Around 1609, a professor named Galileo, he had the idea for this telescope that he wanted to make, but he didn't have the material for it. He needed a glass or a lens to make his telescope work. And so then he relied on the glass makers in Murano to help him. And really all of that, it completely just changed everything, right? So we started using glass, and it helped us start the scientific revolution, right? Because think about this. If we didn't have glass, we wouldn't have telescopes. We wouldn't be able to, say, calculate the orbits, right? Or our planetary system. We wouldn't be able to see planets. We wouldn't be able to make orbital calculations, right? We would still be stunted back into our old ways of thinking in terms of the universe. And on the flip side, we have glass for microscopes, and that enabled us for the first time to see microorganisms. We didn't know that they were like little invisible bacteria, right? How would we have known, right? So glass is so pivotal for even just these two things. In addition, it completely changed the way that we did chemistry, right? Because glass lets us have a contained environment. We have test tubes. Think about how many scientific chemical innovations have been enabled because we just even have test tubes, right? So glass has been such a huge part of our society, and specifically in science as well. So then why is glass so bizarre? And this kind of leads to the question is, why was it so difficult for us to make, okay? And a lot of our recent innovations in glass have actually only been in the last 150 years, and that's because we are just really now understanding the underlying physics behind glass, okay? So that's what I want to kind of talk about now. Okay. So the first thing that we have to understand about glass is this kind of general colloquial description, and that is that glass is, quote, a frozen liquid. Is this an accurate description? It's okay. We're gonna start with it, and then maybe we can expand on it a bit more. So what does this mean? All right, so if we look at the three different phases of of matter, right? We have solid, we have a liquid, and a gas. For a solid, in this example, we have water, right? For all solid materials in general, just go along with me. If you look at their atomic structure, right, they're in a very specific ordered pattern, okay? And when it becomes a liquid, so think about the properties of a liquid. Think about when you have a liquid, it can flow, it can move, it bends, right? And that is also because of the underlying atomic structure. Here, we're no longer confined to, say, a lattice, but here the water molecules have varying bond angles so that they can move, all right? And then for a vapor, we just know that you have singular molecules and they're just floating in the air. Okay, so the atomic structure of a glass is actually of a liquid, but it feels, and everything about it feels and acts like a solid. Okay, so I'm going to expand on that. So glass is made from the liquid state by freezing the atoms in place. Okay, so what does that mean? All right. To really begin to understand what that means, we have to kind of talk about something called a supercooled liquid. So glass is actually from a supercooled liquid, not just per se a liquid. And a supercooled liquid is any liquid held below its freezing or solidification temperature. Okay, so for one example, say we have water here, right? We have liquid water. We know that once we reach 0 degrees Celsius, it will turn into ice, right? But it doesn't have to per se, right? It can actually stay as a liquid even though it's below 0 degrees Celsius. And then when it's in this supercooled liquid form, it requires, you know, kinetics and a little bit of thermodynamics to become then the ice that we're familiar with. And I have this really awesome video that I want to show that gives a great demonstration on what a supercooled liquid is. So if you've ever seen demos of water bottles, right, where they're held at a very cold temperature and then they hit it on the table and then immediately the whole water bottle turns into ice, right? You guys know what I'm talking about a little bit? Okay, well, this video is going to show that. So let's hope this works. Okay, there's no sound. Dan, for the video, is there a way to make this? Did Dan leave? Oh, okay, that's okay. Okay, if not, it's okay. It's just such a cool video. Okay, I did. Okay, that's okay. I'm just gonna talk over it at the same time as it plays. And I think that will work. Okay, so what this guy is showing is he's taking this bottle of water out. It's been cooling for a while, and he's handing it to this person, and he's saying that you have to hit it on the table and see what happens. And immediately what you see happening is that water, that super cool liquid, right? It was perfectly fine as a liquid, but as soon as we applied some energy, it immediately starts to crystallize. And you see it doesn't happen instantly, right? And that's because of kinetics, yeah? Kinetics tells us how fast does it take to reach another state, right? And so what he's trying to explain then is in this super cool liquid, what is happening once you apply some extra energy to overcome an energy barrier, then you're forming these ice crystals and then you will form your crystal or your solid, okay? All right. So let's see. Okay, so I want to try to explain this a little bit in terms of an energy description then. This is how we kind of perceive materials, right? We think about everything in the universe in terms of energy as well as, you know, other things such as physics. But what I'm trying to say is our supercool liquid is what we call is in a metastable equilibrium, okay? So what does equilibrium mean? Equilibrium means it's just in a configuration that it likes to be in. It's at a low energy level, okay? So that's what our supercooled liquid is. Here, this is the free energy across some phase space. But what I'm saying is there's a little energy well here, and that is where the supercooled liquid is. So that's where our, say, our cold water is. As soon as we supply some energy, we overcome this energy barrier, right? This little energy barrier, and now we will form crystals and we become a crystal. And that is at an even lower energy, even more favorable equilibrium, right? So what we're saying is the supercooled liquid, it wants to be a crystal because it is the lowest energy state possible for it. Okay, so what does this have to do anything with glass? All right, I promise we're getting there. Okay, so glass, then, it begins as a supercooled liquid, okay? But in order to make a glass, right? So we're starting from the supercooled liquid. In order to make it, we don't want it to turn into a crystal, right? We don't want it to go over that energy barrier and go into that crystal state. So what do we have to do? What we have to do is we take our molten liquid and we cool it so fast that we freeze the atoms in place. Okay, so think about this, all right? When we're our liquid, okay, we have our liquid atoms and our molecules. But as soon as we let it become a crystal, during that process, it means that those atoms are rearranging, right? They're rearranging into that periodic structure that we would expect from a solid, right? That takes time, that takes kinetics and movement. So what we're saying is we go from a supercooled liquid state, and instead of letting the atoms have enough time to rearrange into a crystal, we immediately stop them from doing so. We freeze them in place, even though it's trying to be a crystal, okay? So, all right, rapid cooling process freezes the atom in place, prevents them from rearranging into a crystal structure. Okay, so this diagram here, this is probably the most important diagram in all of glass science, because this tells us exactly what it means to be a glass. All right, so here we have the volume, we have the temperature, and we're gonna start all the way up here in our liquid. All right, so if we're making a glass, I don't know if anyone's made a glass, but you start with your raw components. Usually it's sand or silica, right? Silica is mainly the backbone of all of our glass compositions. And that starts out as a powder, okay? It starts out as a crystalline powder, all right? We put it into the furnace and then we completely melt it, right? All right, so up here, we're at a very high temperature and it's a completely molten liquid, okay? We cool it down, becomes a supercooled liquid. Now, there are a couple things that can happen. One, if we don't freeze the atoms in place, then that means that they can undergo a phase transition. The material itself can undergo a phase transition, and it'll become a crystal, okay? That's only if we let the atoms rearrange itself from a liquid and rearrange into a periodic order, okay? Now, the alternative, again, I'm just saying the same thing over and over again, is instead of giving them that time, we cool it so fast that the atoms freeze in place, and then we undergo this glass transformation range called the glass transition temperature. And then here we have made our glass. We have a solid chunk of material where when you touch it, it feels like a complete solid, right? But it really just started out as a supercooled liquid. Okay, and depending on how fast and how slow you let it cool, that can result in completely different structures or different properties. The properties can vary a lot depending on how fast you cool it or how slow you cool it. Why? Because depending on how fast or cool or how fast or slow, that tells us how much time are the atoms being allowed to rearrange themselves, right? Okay, so if we can go back to our energy diagram a little bit more and kind of explain what's going on. So again, we're going from our liquid to our gas. What does that mean from an energy perspective? So we're starting out as a supercooled liquid. Well, it just means that we've trapped it in place. And now this introduces another concept about glass that is really, really bizarre. And that is glass is in non-equilibrium. Okay, so again here, when we said that we have our supercooled liquid energy well and our crystal energy well, right? Those, when it's at the bottom of those energy wells, that is the material being at equilibrium, okay? But what we've done is we've moved it out of this energy well, and now it's trapped. It's not in equilibrium anymore, okay? And materials don't like that. Nothing likes that. No one likes to be at non-equilibrium, okay? All right, so what it means is that the glass, which is here, represented by that circle here, it means that glass is always trying to reach equilibrium, okay? And what is the easiest thing for it to reach? Well, it can go back down and it can become a supercooled liquid, because that is what is more energetically favorable than its current state. So glass, every glass that we see and interact with, it's always trying to reach the supercooled liquid. It's trying to turn itself back into a supercooled liquid all the time, okay? And that supercooled liquid, well, what does that want to be? It wants to ultimately be a crystal, right? Because that is what is energetically favorable, okay? So hopefully that makes sense. And something else that we have to talk about then, because of all of this, because of all of these properties, these crazy things, and because it's from the supercooled liquid state, it also means that the structure of the glass, like I've hinted before, the structure of the glass is really unique. And because it's from the liquid state, it means it's non-crystalline, okay? It means that it's non-periodic. So what does that mean? So first, I'm trying to show you what does the opposite of that mean. What does crystalline mean? Or what does an orderly structure mean? So just like from our ice, in which we saw our molecules all orderly and aligned, right? So that is what a crystalline material normally looks like. And so a lot of our everyday materials are orderly, are periodic, are crystalline, okay? So metals, all of our minerals, all of our traditional ceramics, even our advanced ceramics, semiconductors, practically a lot of things have an ordered structure. So what I'm saying though, for glass, is we are not an orderly structure. We are not this, which is what I showed in the last slide. We're actually this. Our long-range atomic structure is completely disordered, is completely random, okay? Which introduces a lot of problems for us, all right? Because it's a disordered structure, that means glass as a material is really, really difficult for us to understand, for us to model, and for us to predict, right? So the ceramicists and the metallurgists, they have it so easy. Are you kidding me? They can predict everything because we know everything about what the structure is. And the structure tells us everything about the material, right? Every property of a material is completely dependent on the structure. Okay, don't tell the ceramicists that I said that their job is easy. They're not. I'm just, okay. All right, I don't want to get in trouble for that. Okay, so a kind of interesting thing that kind of arises. This is a very common misconception and very common myth that I hear about glasses all the time. I didn't actually realize how common of a myth it was until I started talking to everyday people about glass. But the convention is that because glass is a liquid, then does glass flow, and can we observe it flowing, right? Can we say, take a piece of glass that was maybe created, like, I don't know, 2,000 years ago, and can we have seen it move and shift and flow like a liquid, like a really viscous honey per se, right? Okay, and the answer is no. Okay, so yes, it is flowing, and that process has a very specific term in glass science called relaxation, right? Again, because it's trying to reach the super cool liquid. That's why it's even flowing in the first place. It's trying to rearrange itself so it can be at a lower energy level, all right? But no, we would never see any form of old glass flowing because glass flows at about 1 nanometer over the course of 1 billion years, okay? So, and this was actually a really cool study done by my advisor when he was at Corning, in which they completely replicated medieval glass, and they studied all of the relaxation and properties of it, and they measured it, and they put it into this myth once and for all. And essentially the conclusion is it would take us longer than the age of the entire universe to ever be able to visually see glass flowing. Okay. All right, so to kind of summarize this little bit of the section, right? So now we have a little bit more of a nuanced definition for glass, right? So glass, now we can say, is non-crystalline, random order, okay? Is non-equilibrium, and we just talked about that in extensive detail. Frozen liquid that appears solid to us, okay? That's because it takes so long for us to ever observe it flowing. But inherently, it's continuously relaxing towards the supercooled liquid state. Okay, and because of these really unique properties, something that's great about glass is glass can actually be made from any combination of elements on the periodic table, theoretically, if you can cool it fast enough and freeze the atoms from rearranging. You can make anything into a glass, okay? And so because of that, there's about 10 to the 52 possible chemistries for glass, and we've only studied or reported about 10 to the 5th of them, okay? So there's a lot of work to be done in glass science. Okay. And something that really does make our lives very difficult because of all of this. Again, we don't have great models. We can't really predict what's going on because of all of these properties. So a lot of glass research is actually dominated by trial and error, okay? So instead of, maybe saving us time and predicting what a property will be and then designing a glass based on that prediction, we can't really do that as well. We have to just kind of, take some elements here and there. Maybe we increase it by a couple mole percent, and then we make the glass, test it, see what happens, okay? And then we do another round again. Or maybe we'll add a little bit more of another element, or maybe decrease a couple elements, and then we test it again, right? So it's a very iterative, very arduous type of research, but it's pretty fun because you get to work in a furnace lab and like really hot temperatures or dealing with molten lava all day. It's pretty cool. But another thing about glass is because it's at non-equilibrium, this poses a significant challenge, and that's because we don't actually have the math to describe glass that well, because all of our thermodynamics are developed based on equilibrium thermodynamics. Glass is not at equilibrium. You need a whole nother field of thermodynamics, non-equilibrium thermodynamics, to be able to understand glass. And we don't really have, it's in development, okay? There's still a lot to be done. Okay, but even with these limitations, right? And there are a lot for us. It's so impressive that we as humans have been able to manipulate glass and understand it to even just the limited amount of understanding that we have. And we've been able to completely create these amazing products that we have incorporated in our everyday lives. And we're still learning, we're still getting better at making them. So some important glass innovations that I want to highlight. The first one, which is probably the most important, is the development of fiber optic cables, okay? So fiber optic cables is made of a very specific type of engineered glass that we as humans have developed. It's mostly made of germanium or germanium oxide and silica. And what's really great about this is that it lets us transmit light without losing a bunch of that signal across the way, right? So light or our signal comes in and it can be internally reflected. And so what we can do is we can carry data all the way across to another continent. So this is a map of all of our major fiber optic connections around the globe. And this enabled us to have the internet. This is why we can communicate with somebody all the way in Japan in an instant, right? And it's all because of glass and specifically fiber optic cables. Okay. Another one that's really important is liquid crystal displays, right? This, I mean, it's so prolific. We deal with it all the time, right? Even just on a calculator or even just on, say, a watch face, right? These are all made with specialty glasses that we have specifically developed. And something specific that we have to consider with, say, like really big displays is we have to know how much is that glass going to relax, because when we embed pixels in it, right? If the atomic structure in the glass is moving because it's cooling, because it's undergoing relaxation, we need to make sure that those pixels don't get affected and that they don't get lost, right? And that they don't get broken. Something that we might not really think about that much, but that is really important, is the development of cell phone screens. At least I remember when the first like cell phone like this came out, and it wasn't just a flip phone, but when those first cell phones came out, if you drop them even once, the whole screen would shatter, okay? That's how bad our glass used to be for cell phone screens. But now think about how many times you've dropped your cell phone. Do you even think that's gonna shatter? Maybe you're maybe worried, but most of the time, no, it's perfectly fine, right? And even back then, the screens would just shatter even if you had like keys touching them, keys rubbing on them, if your cell phone was in the same pocket as your keys, right? We don't even think about that anymore, right? Because our glass is so good now. And this specific piece of glass, right, this was developed by Corning. It's called Gorilla Glass. This is what my advisor and an entire team of engineers worked on at Corning. And it's a very specific chemical composition. It's alumina and silica and other things that we aren't allowed to know because it's patented. But another thing that is really cool that a lot of people might not be aware of is bioglass. Bioglass is really neat. And this is just tiny glass fibers, all right? And what we can do is you can actually all group them together like this, and it looks like a cotton swab, right? And so what we're doing with this was developed in the 1970s. What we're doing with this is, because it has a chemical composition that's very similar to, say, your bone or tissue, we can put it on wounds, okay? And we can use it to help bones grow, all right? Your bone and your body will use it as a scaffold to help your bones grow. And it'll actually help heal your tissue over time, okay? So this is what bioglass is used for. Okay, last slide, just some, okay, no, 2 more slides, sorry. Some other common glass products that we have that I just want to make you aware of is our wind turbine blades. Those are a form of aluminosilicate fiberglass, all right? Think about how much force a turbine blade has to withstand. You need a material that, yes, it has to be somewhat flexible, but it has to be insanely durable too, right? And that is what we can get with glass, okay? Some other very common things, modern day cooktops, right? But also space shuttle tiles. And we still use this to this day. That is glass, right? Think about what the space shuttle tiles have to withstand. They have to withstand insanely high temperatures. Well, glass is great for that. All right. The other thing, medicine vials. So right during COVID, we actually had to re-engineer, specifically Corning had to re-engineer its medicine vials because they were too fragile to withstand the mass production of us having to create them and ship them out. So they actually had to re-engineer them to be stronger so that when they rubbed against each other, the vials along, say, like a manufacturing line, they wouldn't shatter, okay? All right, so just quick, very briefly, 2 slides about glass research today and kind of the future challenges within this field of research. Okay, so these are just 3 main goals of glass research. There's so many areas of glass that we don't understand, that we are always actively learning. But these are just 3 of the ones that I really think are important. The first one is, how does water impact glass? Okay, so water actually is absolutely detrimental to glass, all right? Which is why you should not put your wine glasses in the dishwasher, even though I definitely do because I'm lazy, but you should not, because we know that water actually chemically attacks the surface of the glass, okay? And so, but we don't really understand all of the mechanisms for it. It's very, very weird and complicated. And so what we've done is we can use some more modern day approaches now. We can use atomistic simulations. So this is a molecular dynamics simulation that I did during my graduate studies. And what I'm doing is I'm studying what happens to glass when we, say, have a water molecule on top, and what happens if we simulate fracturing of glass, and how are those glass atoms going to be affected by the water that's all above it in the fracture point. All right. And then something else that we can do with modern day approaches, we also have quantum mechanical simulations that we use now. So this is a simulation that I did I think a year ago, I don't remember, but this is me using quantum mechanical simulations to look at infrared structure of a luminosilicate glass and to look at the different coordination states within the glass so that we can understand what is the underlying structure. And the beauty about simulations is it's very cheap compared to doing it the experimental way. So that's where simulations really shine. But we have a lot of advances in experiments as well. The main one that has been really revolutionary in terms of helping us understand glass structure is the development of nuclear magnetic resonance, okay? So this fancy piece of equipment, it's usually like $100,000, goes up to $1 million worth of equipment here. What it does is it uses a very powerful magnet, and all we're doing is we're manipulating the magnetic spin of our atoms of the nuclei within our glass. And what we get then is a specific response as the spins relax. We get a signal back, and we get some spectra, and it tells us what is the coordination, what is the atomic structure of our glass sample, right? And this is how we're slowly beginning to understand the structure of glasses, no matter the chemistry. Well, it has to be NMR active, but anyways, in summary, glass is really weird, and I hope that I've highlighted that, and I hope that I've kind of elucidated why it's so strange, but also just how cool and bizarre our understanding of it is, and just how fascinating it is from a physics and thermodynamics perspective, okay? And last thing I'll say is glass is always going to be around. So, and there's so much to study with glass. So for all the students in here, if you want to get into an amazing field of research, join the science department, or glass science department. Yes, join our glass science department, which is at Alfred, which does amazing glass research. You won't regret it because it's really cool. All right, thank you.
What questions do we have for Rebecca? And I'll count on you all up in the booth to let me know if there are questions in the Zoom, if my Wi-Fi craps out again.
Thank you. Wonderful talk.
Thank you.
Several times you talked about how the molecules are trying to do something when you were
Yes.
talking about the relaxation
Yes.
blood crystal. But that's a metaphor. Could
Mhm.
you, I'm not a physicist, but could you explain that without using the metaphor of trying? Could you explain what force is driving them to?
No, that's a great, so it is an overall driving force of trying to reach equilibrium. So we are actually, so the energy description is in fact what is going on. We are trying to constantly reach equilibrium with the atoms in the glass, and that is the process of relaxation. And that's something that we actually are still trying to understand today. There's a lot of glass relaxation models out there. And so far, we've been able to predict that it has a decreasing exponential function, but it's a very specific exponential in that it's like a lagged exponential decay. But that's like the extent that we really understand about it. So it's yeah, that's honestly, it's really something that we're still understanding, and we just have a very rather simplistic model for how to predict it. But even then, we can't even apply it to a lot of glasses. So we have to just rely on experiments, and usually for that, it's just take a chunk of glass, see how much you can either see how much the refractive index changes in it over a function of time, or see how much, say, the volume shrinks over a function of time. And then that gives us how fast is it relaxing. But otherwise, yeah, that's really what's going on, yeah.
A few years ago, I was on a evaluation team, mid-states accreditation evaluation team at an engineering school in Philadelphia, Drexel University. And the year that I was there, Drexel had finally eliminated a required course for freshmen in calculus. We were all a little surprised by that.
Yeah.
And just recently, I'm reading something to the effect that students in China, the equivalent of sophomores in high school, are studying calculus, but American high school students are making videos, stupid videos for TikTok. And so my question is, to what extent do we find the science of glass technology that you're really dealing with here, that other countries are beginning to eclipse what we're doing here in the United States? Does this become a problem that is, in a sense, national and future?
That is a really, really great question. In terms of glass science, innovation, I would argue that the United States is the best, and it's because companies such as Corning, they dedicate millions and millions of dollars each year to just glass research. And something that actually is kind of a problem in industry is what we've seen is these outside countries, specifically China, they actually try to get jobs at Corning and then try to take Corning's IP. So when I was there as an intern, they had just undergone this gigantic scandal, actually, where this employee, this research scientist, he was secretly selling Corning's IP of their fiber optic cables back to China in exchange for millions of dollars. And Corning found out because they track every single email, every single text message, everything when you're there. Yeah, it's interesting. So I wouldn't say, it is sad that one school got rid of calculus, which is really unfortunate in the engineering program. But otherwise, I don't know. I can't really comment on per se how other universities are advancing or not advancing compared to the US. But one thing I will say, though, is a lot of people that like physics, a lot of people that come from a physics background, they actually end up in glass. A lot of us are actually like physicists by heart. And then we find glass, and because it's so interesting and so weird, and because of the non-equilibrium behavior of it, we like to apply our own, computational models and typical physics approaches, and we apply it to glass, which is why we actually have a lot of our current models now, which are all based on fundamentally derived physics principles. So, yeah. Okay, sure.
Sorry, I have like a two-part question, if you don't mind. So the first is, I was fascinated by a thought that you shared, one of the earlier slides about the Romans and the Western world was focused more on glass, and the Eastern world in Japan, for example, like like shoji doors was like thinking more about paper. And I'm not in this field at all, so my bare bone understanding of glass is like kind of heat and minerals that turn into crystals and whatnot. What the other side is water and plant materials that turn into fiber. So there's like this contradictory or complementary dynamics that happening on both sides of the world. And I was just curious about whether or not you kind of have more thoughts on that, or like have more research on like the differences between the two. And then the other, sorry.
Yeah, it's a great question. And no, I am not a historian by any area. So no, I don't know if I can comment on per se the historical.
It's more
perspective,
about
but
curiosity, but
yeah. Yeah, but going with your comment though, so I'm not sure if I understood what you were saying initially, but paper and like that fiber from paper is very different than say like fiber
or
optic
just the
cable.
materials and how they both are made are quite opposite to each other, and versus the Eastern versus the Western geographical as well. That yeah.
We make glass because of the minerals that were around us, right? So a lot of glass traditionally was made from sand. So Egypt, there's a lot of sand, okay? So naturally, right, started playing around with sand, and if you heat it up and kind of manipulate it, then you can turn it into a glass. It's not a good glass. It's very, very bad, actually, very impure. But a lot of like the Romans around that area, they had very specific minerals like quartz and calcium carbonate, sodium carbonate that were really, really great for glass. So yes, that does bring up an excellent point in terms of like what is available geographically. Yeah.
And if you don't mind, the second part of my question is like, I was just curious about your like origin story of like, how do you come across this subject of studies, or like what got you into this?
Honestly, the only reason why I got into glass is because first, I really liked physics. So then naturally, I wanted to go to a college that had a physics program. The only one that had one was that was in my hometown was Coe College. So Coe College had a physics program, and I was like, okay, I like physics, I'm going there. And then it turned out that within the physics department, their entire department did glass research, and I had no idea. And all the undergrads did glass research. So I was like, oh, okay, I guess I'll do it. And then you just like fall in love with it because you do it and you learn to love it and you learn everything about it. And then you're like, I want to know more. And then ultimately, that's kind of where you find your passions. It's just usually people become passionate once they begin to know a lot more about one specific topic. Yeah. Mm-hmm. Oh,
Hi.
sure.
Hello. So in that energy model that you showed us with the ball and the like
Mhm.
pump in the middle and the two
Yeah.
energy pools,
Uh-huh.
you kind of show like a little nudge of energy that's being given
Uh-huh.
to this substance before it goes back to the super cool liquid.
Uh-huh.
What would happen if you like put more and more into that, not until it like would go over that hump to become crystalline, but like, is there anything that goes on if you just like keep pushing it, not until it reaches that point, but the farthest it can go?
That's a great question. Let me think about that for a second. I'm not entirely sure. Yeah, that's a really great question, but I don't think so, because it kind of is just kind of like a figurative kind of visual. But in terms of like where you are along that little segment of that hill, it could be like Honestly, I don't know. I'm not sure. That's a great question. Yeah, I don't know how to answer that one. Yes. Okay. Oh, yes, yeah. Why is it thicker than, because that's what we saw in our medieval glass. That was just how glasses were made back then. So when we make a glass as an artist, okay, you have this long pipe, right, where you blow air into it, and then you have a glob of molten glass at the end, and you blow air to it. If you blow into air to it, then it can become a bubble. But if you don't, and if you spin that long tube that is holding that glob of glass, if you spin it, if you can visualize, because of the centrifugal forces, it's like spreading out. Okay, so it becomes thinner at the edges and you get like this huge circle of glass that's thin, but then near the tip of where that rod is, it's thicker there. And so then, at least this is what we have all agreed on, is that the window makers, they just put the thicker part at the bottom. That's it. That's literally it, yeah.
Done.